So now we have the last talk of this session, which will be given by Rob, who works for US Naval Research. I think most of you already know him. So let's just get started with the final talk.
All right, thank you. So I'm going to talk about data-explainable website fingerprinting with network simulation. This is joint work with my colleague, Ryan Wales, who's just up here. Another version of the title is How to Accelerate Your Website Fingerprinting Research. Hint, I'm going to tell you to stop crawling the Tor network and use network simulation instead. There are a variety of advantages, which I hope will become clear throughout the talk. We all know what Tor is. It's an anonymous communication system, provides anonymity to its clients by preventing an adversary from linking the client to the destination. So one of the major attacks against the Tor network is a website fingerprinting attack where an adversary that can observe traffic between the client and the network can de-anonymize the client by predicting the website. And the requirements in this attack are the adversary must be in a position to observe traffic between the client and the network. And because the adversary uses machine learning models in this a prediction task, it needs labeled data so that it can train its models. Fortunately for us, Tor encrypts traffic, so the adversary does not have access to the genuine labels in the position that it's viewing the traffic, so it needs to get this information from somewhere else. So where is it going to get this data that it needs for training? The traditional method, which has been used almost exclusively in website fingerprinting research, is to use an automated browser crawler called Tor Browser Selenium to crawl websites over the Tor network, collect traces and labels, and then use that data to train the machine learning models offline. The idea is that the adversary can repeat this over time to stay fresh as websites are updating over time. I argue that this approach produces low-quality data sets because there's a variety of variables that are changing that are affecting data quality. The left column here has been talked about by Mike Perry, Mark Juarez, and others a decade ago, things including browser version, configuration, which URLs you're choosing to browse, how many tabs you're using, geolocation, data staleness, etc. Less often considered are the variables of the network itself, including relay churn, the joining and leaving of relays, relay version, relay configuration, and relay congestion, which can be caused by a variety of factors, including natural usage fluctuations, denial of service attacks, and other things. So researchers are really using the Tor network as a black box data set generator, but we have very little control over the network. We don't really understand the data that's coming out of this, and so this causes frustration for myself personally, and that's why this paper is about. We're trying to understand how the changes in the network are affecting website fingerprinting attacks. So our research direction is to explore creation of more explainable data sets. We're going to use network simulation to increase control over data set production and collection process. We're going to use that data to augment the training process to produce more diverse data sets and to help us explain causal relationships in website fingerprinting results. So we have 3 research questions that we explore in the paper. How well can we do this in Shadow? We're going to use Shadow for simulating things. How sensitive is website fingerprinting to changes in network conditions? And how can classifiers be made more robust to network effects? So the first research question, how can we do this in Shadow? We set up a measurement experiment on the Tor network, or on the internet. We set up a Wikipedia mirror, which gives us access to 23 million pages, and a relay that we patched to export the patterns we need for website fingerprinting. Then we chose 98 pages at random from the Wikipedia mirror and fetched each page 200 times. One wrinkle is that Firefox is not yet supported in Shadow. Hopefully that will be coming soon. So in the Shadow experiments, we need to use wget2 as a replacement for Tor browser. And so we produced 3 data sets here. One where we use Tor browser on the Tor network, one where we use wget2 on the Tor network, and one where we use wget2 in Shadow. So the first thing we look at is how well does wget2 serve as a replacement for Tor browser. So both of these data sets are from the live Tor network. We look across a variety of features, and the main thing to take away here is that the distributions are significantly overlapping. And we also verified that the resources requested by wget2 were exactly the same as the ones being requested by Tor browser. So this gave us enough confidence to proceed with the research. Then we set up a classification experiment. This is using wget2 data from the Tor network and wget2 data from Shadow. we set up a multi-class closed world experiment, and we were just looking at how easily can the websites be predicted. So 1 out of 98 would be a random guess. And what we find is that we have very high accuracy, especially when training and testing on data from the same source. So when training on data from Tor and testing on the same data set, we get 97% accuracy. And then in the shadow case, we get nearly 100% accuracy. Another interesting highlight here is by training with data exclusively from simulation and then testing on the traces that we gathered from the live network, we have a classifier that achieves greater than 85% accuracy. So this is, I think, the first time that's ever been done, and I think is very cool. All right, moving on to research question 2. How do network effects affect website fingerprinting? So Tor is constantly changing. Both the network is changing, new relays are joining, old relays are leaving, and congestion is highly variable. And so we model this scenario in Shadow by creating 9 different Shadow private networks. We create a baseline network, and then we subtract 25% of the background traffic. That's a low congested state. And we add 25% extra background traffic. That's a high congested state. And then for each of those congestion conditions, we generate a new network by re-randomizing the relays that are chosen to participate. This sort of models how Tor changes over time. So in total, we have 9 different networks here, and we can analyze what happens when training in one of these networks and testing in a different one in both directions here. Just really briefly, we did a performance analysis to verify that how the congestion is changing as we actually increase the traffic on the network, and we verified that indeed, as you add more load to the network, download times in the network get significantly higher. So this is indicating that congestion is occurring. Okay, so then we created some data sets, one for each of these networks. We then, from this data sets, collected website traces. We labeled sensitive. There's a website set labeled sensitive by the adversary. We chose 5 pages and crawled those 300 times each. And then we have a background data set containing 30,000 web pages that we crawled as well. So the classification experiment here is a binary open world classification experiment. We're just wondering, when we see a web page, is it in that set of 5 that we called sensitive or not? And we trained 4 classifiers in each of these 9 networks. That gives us 36 classifiers. And for each of those, we test them in each of the 9 networks. So we have a lot of results. I think there's like 4 pages of results in the appendix in our paper. So I'm only like giving you a drop in the bucket here. But one of the main results we found was that variable load has a much greater effect than a variable seed on website fingerprinting accuracy. Here for K fingerprinting, we observe a 19-point drop in the true positive rate by training in a baseline network and testing on a differently loaded network. We also noticed that training on a lowly loaded network, with low congestion, and then testing on a highly congested network performed particularly poorly. Second, we found that the average false positive rate increases more for time-aware algorithms. K fingerprinting and TikTok both use timing information in addition to patterns. And we see a 400% to 500% increase in the false positive rate for those classifiers. Okay, the final research question is, how can we make website fingerprinting more robust to network effects? So to do this, we created a mixture training experiment where we're mixing data that we gathered from multiple of our 9 networks and then testing in an independent network that we didn't use to train. But we're allowing us to gather data from multiple of the simulated networks to make a more robust classifier. And we find that this approach works quite well. For the TPR, we see single to double digit increases in TPR and double digit up to 83% in the highest case reduction in FPR. So this, for our case that we looked at, this does increase, make a more robust classifier that is better at the task. Finally, we brought this full circle and we took this robust classifier that we trained in simulation and we went and tested it again with those Tor wget traces that we gathered that I mentioned at the beginning of the talk. So the robust training classifiers are again trained with 100% simulated data. And we found that this doesn't work very well for the classical algorithms for Camul and KFP, but it does work well for the neural networks, and especially well for the time-aware algorithm, the TikTok algorithm, likely because we have a more diverse congestion data set that we were using for training. And that's all I have. The advantages of this approach: we can do this with a perfectly privacy-preserving approach. Shadow is completely offline and has no risk or load to the real Tor network. We get an unlimited source of accurately labeled data by using a simulation, higher data diversity. The controlled network means we can have a more explainable data sets and hopefully be able to better explain our results. And we found that the simulation-assisted website fingerprinting outperforms standard methods. Future work, we want to actually do this with Tor browser, not just wget2. And we want to expand beyond just one site. We use Wikipedia because it gave us access to 23 million pages instantly. But we want to look at other sites. And then I think an independently useful thrust is to study website fingerprinting on the live network using genuine data. That gives us a better threat estimate of how website fingerprinting will work on the real network, like in practice. That's all I have. Thank you.
Well, thank you for the very interesting talk. And we have one question from Florentin. Could the new client-side implementation of Tor, RT, affect website fingerprinting differently than the existing implementation of CTOR? Even more so, do Shadow support setting up different client-side Tor, RT, CTOR, CTOR version X, or maybe some version X plus one?
I think RT is basically using the same protocol as the CTOR client, still implementing the same circuit building process. So I don't see immediately how that would affect things, other than maybe being more configurable or differently configurable than the existing client. So maybe some of those different configuration options would affect things, or maybe they change the protocol or extend the protocol in some way where RT supports more features than the old C client. That might affect things, but otherwise, I don't see why that would make a big difference.
We have another question from Vera. Based on your findings, what can be said on the utility to noise ratio of timing information used by deep neural networks? Can it then be that deep models using timing are overfitting to the networking conditions as opposed to extracting an actual fingerprint?
Yeah, so that's my argument, I think, for the live network. It's overfitting to that one data set that you're using. I'm trying to explore across different networks with different timing features across the network, so it's getting a more diverse data set. Now, I think if the question is it overfitting to just those 9 simulated networks, then we could, I would argue, create more than 9. Nothing stops us from using 9. We just did 9 in this first experiment. But we could also try mixing data from the live network with simulated data, try to augment and use both of those data sets to create a super robust website fingerprinting. So that's another direction for future work, I think.
Thank you so much. And we also have time for one more question if someone has any. Yeah, so there is one. Who is a typical attacker in this scenario? So this is a question by Linus Gasser. Who is a typical attacker in this scenario, as they can only get an answer like, this user might be looking at this website. Who would use this?
Good question. This, I think one of the main places where this would be used is in censorship. So if you can guess the website that a user is visiting, and you know which website it is, and you don't want the user to be visiting that website, maybe you're trying to block access to a specific Wikipedia page on Falun Gong or some other historical event, and you don't want people to access that from your network, that would be a typical use case for website fingerprinting attack. It also breaks Tor's anonymity, so we don't want that.
I think let's thank the speaker, and yeah. This brings an end to our session, and I would like to just thank Lev and Boya for making sure that all the transitions between remote and the online presentations were smooth. So yeah, we can have a half an hour break.